Hello, this is Miraj Patel, and today we're going to be starting Unit 6, which is all about covalent bonding, which is the second type of bonding we haven't talked about. And today we're going to be talking about what are covalent bonds and how to draw the covalent bond structures. And covalent bonds, first of all, are formed by sharing electrons between non-metal atoms only. And so the difference between ionic and covalent is only between nonmetals, and ionic in the last unit was between metals and a nonmetal. And a molecular compound is a neutral group of atoms joined by covalent bonds. So these would be examples of molecular compounds. And so here we have two examples of covalent bonded compounds. And so here we have water. So now you know water is a covalently bonded molecule, and carbon monoxide. And notice how there's two nonmetals bonded together. And here are some common elements that are diatomic, which means two atoms of the same element. So a diatomic molecule is a element that exists with two atoms. So like notice how whenever if you've seen oxygen before, most people say O2 because O2 or oxygen is a diatomic molecule. And so here are the 7 diatomic molecules I have to remember: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And so a good way to remember this is the lucky 7. So think of a 7 and then just hydrogen over here. So just think of the lucky 7 diatomic molecules. And so a molecular formula shows how many of each atoms of each element there are in a covalently bonded molecule. And so here are examples. So molecular formulas would be like H2O, CO2, C2, H6O. So these are all examples of molecular formulas because they tell you how much of each element we have in one covalently bonded molecule. And so this is different from ionic bonds, and the formulas for ionic bonds are called formula units. So don't get confused between molecular formula and formula units. Molecular formula is for covalently bonded, while formula units is for ionic bonding. So those are different. And so here we have H2O. It tells us there's 2 hydrogens and 1 oxygen atom in each atom. Then we have carbon dioxide, CO2, 1 carbon and 2 oxygen, 1 atom, and then ethanol, 2 carbons, 6 hydrogens, and 1 oxygen in each atom. And then here are some properties of molecular compounds. They have lower melting points than ionic compounds, and usually solid or gas. It's like usually getting to solid or gas. And they're poor conductors. So you know how I was talking about how water doesn't really conduct electricity by itself, but like the ionic compounds in water conduct electricity. So this is why water is a very bad conductor, because it's covalently bonded, and covalently bonded molecules are poor conductors. So moving on. So here we have formulas and models. So there's several different types. So here we have the molecular formula, which we just talked about, tells you the number of each element in formula or in the molecule. Then we have the space filling model, which is like the bunch of huge spheres stuck together. And then we have a perspective drawing, which shows us the shape of the atom, how it would look. And so notice how these lines are just like bent, and these arrows like tell us if it's coming out at us or inwards and stuff like that. And then we have the ball and stick model, which in college, there's in like chemistry classes, they have to make models, and so this is how it came. So you pretty much have a bunch of balls with holes in them, and then you have sticks to join them, which represent bonds. And then we have the structural formula, which we'll be learning about in the next PowerPoint and how to draw them. And so here's a quick quiz to see what you learned. 1. A molecular compound usually consists of 2 metal atoms and a nonmetal atom, 2 nonmetal atoms and a metal atom, 2 or more metal atoms, or 2 or more nonmetal atoms. And so a molecular compound, first of all, is something that's covalently bonded, because we just talked about that at the beginning on the first slide. It's in molecular compounds, like are covalently bonded. So covalently bonded molecules, the special part is that they only contain nonmetals. So nonmetals only. So any answer that contains metals is incorrect. So by default, D is the correct answer, because this is the one that says it's only nonmetals. And so remember, metals are for ionic compounds. This is nonmetals for covalently bonded. And so a molecular formula shows A, how many atoms of each element a molecule contains, B, a molecule structure, C, which atoms are bonded together, D, how many atoms are arranged in space. So if we go back to the slide, so a molecular formula is this thing, and we talked about how this thing only shows the number of the types of atoms we have in the number of atoms. See, this would show how it looks, and then this would show the structure, so just the structure, and this one gives like a visual appearance of their atom sizes, and these other ones again show structure and sort of angles and stuff. So the correct answer for molecular formula shows is how many of each atoms there are in an element. So just think about the little formula like H2O. From that little piece of information, you can just tell how many of each atom we have in that molecule. Because you can't tell structure, you can't tell which ones are bonded together, or how many atoms, how the atoms are arranged. Those are different models. And so 3, compared to ionic compounds, molecular compounds tend to have a relatively A, low melting points, B, high melting points, C, high conductivity, or D, low conductivity and high melting points. So remember on that slide we talked about how how molecular compounds are they don't really conduct electricity or heat well, and the other fact was that they have lower melting points than ionic compounds, because ionic compounds have those tight, negative and positive attractions, so they really don't want to release from each other. But these don't have that as strong, so they have lower melting points compared to ionic compounds. And so that brings us to the second PowerPoint, which is all about writing the formulas and structures. And so covalent bonding and Lewis structures. So we're going to combine Lewis dot structures and make actual structures of atoms. And so here, like in ionic bonding, the whole point of covalent bonding is to get 8 electrons, and that's called the octet rules. Atoms form bonds to have 8 electrons in their outer shell, like noble gases. And so here you can see like a visual of the octet rule. So here we have fluorine, and fluorine, how many valence electrons does it have? It has 7 valence electrons, because it's in row 7A. And here we have another fluorine atom. And so these atoms both have 7, but they want to get 8, so they need one more. So they just share it with each other, and we get this. So notice how there's 8 electrons in this orbital and 8 electrons in this orbital. And so this is an example of a diatomic element. So fluorine is one of those lucky 7. And so again, octet rule. So atoms want to form 8 electrons, just like this fluorine did. And so here's another visual of the same thing. So we have 7 valence electrons, and these are called Lewis dot structures, like we talked about from a few units back. And so they want 8, so they form together and they share these 2 electrons. Or you can write it like this with a line. And here's some important terms to know. So here, this is called the shared pair, or like the bond inside these 2 electrons. And then the pairs that aren't shared are called unshared pairs, or non-bonded pairs, or lone pairs. So if you see any of these 3 words, they mean the exact same thing. They just mean the electrons that weren't shared, and they're in pairs. So this would be one pair, this would be one, this would be one. So it's always important to know that these are pairs, not just each individual electron. And here on the electron configuration, you can see the same thing. So 1s is the inner level, so this is the valence level, and so we have 1, 2, 3, 4, 5, 6, 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons. So these two will be shared, and that's how we get this octet for both of them. And a single bond is just one pair of shared electrons. So this would be an example of single bond because there's only one pair of shared electrons. And here's another example of H2O, so just water. So we have 2 hydrogens, each with one valence electron. Then we have 6 valence electrons from oxygen because in group 6A. So these hydrogens put in their electrons right here and here, and they form this structure. So notice how there's 8 electrons, but hydrogen only needs 2, so that's why hydrogen only needs these 2 each. So, or it could form a structure like this, 2 electrons, 2 electrons, and this represents 2, and this also represents 2. And from this is called the structural formula because it shows the arrangement of the atoms. And from this, we can see the number of unshared pairs. So we can see one pair here and one pair here. And so we have 2 unshared pairs. And we can also see unshared pairs from here too because there's 1 pair, 2 pairs. And then let me ask you how many shared pairs are there, or bonded pairs. So everything else is bonded. So this would be one pair and this would be one pair. So there will be 2 bonded pairs also. And again, you can see from this electron configuration also. And this is the ball space model, so you can see how it actually looks. So the oxygen is so much bigger than these 2 hydrogens. And then we have ammonia, and again, you can see how the hydrogens fit in here and share their electrons with nitrogen. So nitrogen gets 8 and each of the hydrogen gets 2 because hydrogen only has 1 ring and 1 electron, so it can only get 2 electrons. And so again, how many shared pairs are there, or unshared pairs? So there's 1 pair of unshared pairs, but this has shared pairs, so there's 3 shared pairs. And again, you can see from the electron configuration that nitrogen has 5 valence electrons, and again, you can check that by looking at nitrogen, which is in group 5A, and then we have 3 hydrogens, so 1 electron shares here, 2 here, and then 3 here. And then this is again the space model to show how it looks. And so here are some examples of double bonds and triple bonds. Double bonds are 2 pairs of electrons shared. Triple bonds are 3 pairs of electrons shared. And so this will be 1 pair, this is 2 pairs, and then this is 3 pairs. And again, these are also examples of diatomic molecules. So remember the lucky 7: oxygen, nitrogen, fluorine, chlorine, bromine, iodine, and hydrogen. So these are 2 more diatomic bonds. And so here now we're gonna talk about special carbon. And the special thing about carbon is it has 4 valence electrons and it needs 8, so it can form 4 bonds instead of 1, 2, or 3. And so because carbon can form 4 bonds, it can allow the formation of large biomolecules like proteins, lipids, carbohydrates, and nucleic acids. So there's a whole branch of chemistry called biochemistry, which is just devoted just to carbon. And so here are some. So when you go in biology class, know that carbon is super special and it forms a backbone of pretty much every single compound in biology because it can form 4 bonds. And so now we're going to talk about how to draw these. And so we've been looking at them, but how exactly do you draw these structures? So there's 4 easy steps. So first, we have to count the valence electrons of all the atoms in this compound, because the whole point of the structure is all about valence electrons, so we have to count the valence electrons. So phosphorus, which is P, has 5 valence electrons, so 5 right there. And then chlorine, each chlorine atom has 7 valence electrons, so times 3, which is 21. So 21 plus 5 is 26. So that's how we got that answer. So next step, the central atom is the least electronegative, so the most left and to the bottom as possible. So we put that in the center, and then we just connect the lines. So this would be an example. So we just connect all the elements, and so each line represents 2 electrons. So 1, 2, 3, 4, 5, 6. So we just took up 6 electrons. And so while we do this, we have to keep track of the electrons. So because we use 6, we subtract 6 from 26, the total number of valence electrons and how many we use, and we have 20 left. And so with those 20, we fill the outer octets first. So we add as many electrons we need for the outer atoms, so they get to 8. So 1, 2, 3, 4, 5, 6, and this bond is 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So here we use 6 times 3, which is 18. So we used 18 more electrons. So we have 2 left. And then we finally fill the octet of the central atom. So here we have 2 left. So we put those on the center. So 1, 2. And then 2 minus 2 is 0. So we're all good because all these atoms have 8 electrons. And then here's another example. So HCN. So we're going to do that one. So here, let's just do it so as after we saw the structure. So just first you could count the valence electrons. So 1, 2, 3. So 1 valence electron for hydrogen, 4 for carbon, and 5 for nitrogen. So we have a total of 10. First, we put the least electronegative in the center, which is carbon. Hydrogen is actually a little bit more electronegative than carbon, so it's different. And then we connect them, so 1 bond here and 1 bond there. So this would be 4 electrons lost. Then we fill the outer octets first. So 1, 2, 3, 4, 5, 6. Because we used 4, we had 6 left from 10. So 10 minus 4 is 6. And we put the 6 here. But the carbon is not satisfied because carbon still needs 4 more electrons. And so this is the 5th step. So if you run out of electrons before the central atom has an octet, then we have to form multiple bonds like this until carbon is satisfied. So here we took this pair and shared it with carbon. So carbon has 1, 2, 3, 4, 5, 6 electrons, but we still need another pair. So we have to take another one and we form a triple bond. So this is an example of a triple bond because 3 pairs are shared. And so this would be the final structure. And so here, draw the Lewis structure for trichloromethane. So let's just see if you get the same answer. So feel free to stop the PowerPoint and try this on your own. So let's just go through this. So first, we have to count the number of valence electrons. So carbon has 4 valence electrons, then hydrogen has 1 valence electron, then chlorine, each one has 7, so 7 times 3 is 21, so 21 plus 1 is 22, and then plus carbons, which is 26. So we have 26 electrons total, and then first we put carbon in the middle, because carbon is usually the least is the least electronegative. And then we attach all of these around carbon, because carbon can form 4 bonds. So if we use 4 bonds, that would be 8 electrons lost. So 26 minus 8 is 18. And then, so 18, and then we add those 18 left electrons. We try to fill out the outer octets, and so each of the chlorines gets 6, and so 6 times 3 is 18, so it works perfectly. So we added 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it worked perfectly, and hydrogen doesn't need anything because hydrogen can only form 1 bond. So a key trick is, remember, hydrogen can only form 1 bond because it only needs 2 electrons. And so here we have one more example. Draw it for CO2. Draw the Lewis dot structure. So first, again, we count the valence electrons. So 4 is carbon, and then oxygen has 6 each times 2, which is 12. So 4 plus 12 is 16. Then we put carbon in the middle, so C over here. Then we attach oxygen to it. So 2 bonds would be 4 electrons. So 16 minus 4 is 12. So we used the 12 electrons to fill up the outer octets. So each oxygen would get 6. But the carbon in the center would not be satisfied. And so that is why carbon has to form double bonds. And so because each oxygen had 6, so imagine a pair here and just 1 bond missing, and a pair here and 1 bond missing. But because each atom is equal on both sides, we have to take 1 from one side, and then if we need more, we have to take 1 from another side before we can take 1 from the same element. So if they both have the same electronegativity, or they're the same element, you have to equally take if you need more. So you can't just take 2, you can't just have a triple bond here and 1 bond here. You have to balance it out because they're the same element. So just as a side note. And a good way to check is always count the number of electrons each element has. So here you can count 1, 2, 3, 4, and each bond is 2, so 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So carbon's checked, oxygen's checked. 1, 2, 3, 4, 5, 6, 7, 8. So the other oxygen is checked. And you can even do this for this one, and it should always work. And so except for hydrogen, which only needs 2. And so here's a quick quiz to see what you learned. Carbon atoms have 4 valence electrons to form up to 4 bonds. This allows carbon to form blanks needed for life. A. Large long chain biomolecules. B. Nucleic acids. C. Carbohydrates. Or D. All of the above. And so this question was from that one slide which talked about carbon. So carbon is special because it forms large biomolecules, and the whole study of carbon in atoms is called biochemistry. And examples of biomolecules are nucleic acids and carbohydrates. So the answer is D, all of the above, because biomolecules include these two. So by definition, all of these have to be included. And so, which of the following diatomic molecules has a triple bond? And so let's draw the Lewis dot structures. So O2, so oxygen has 6 valence electrons, each, so times 2 is 12. So we have 2 oxygens, put them side by side. And here, let's just show you all the dot structures. So we had 6 valence electrons, so we first bond them together, then we try to fill up the sides. So we would have a remainder because one side would be filled, but the other side would have one pair missing. So we would have to balance it because these two elements are equal. When you do the octet, you have to start from one atom and then do it to the other atom equally. So you would add 1 pair here, 1 pair here, 1 pair here, 1 pair here, and then you would add 1 pair here, which would be unfair because this one would be filled, but this wouldn't. So you would have to take that pair and erase it and then make a bond here. And then here we have nitrogen. Nitrogen has 5 valence electrons each, so 10 valence electrons total. And so first you would draw a bond connecting them, and then you would pair up electrons on both sides. So you do 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10 would be that middle pair, a little middle pair, sorry. And then that wouldn't work because it would only have each electron would only, atom would only have 6. So you have to take some of those pairs and make some bonds. And then bromine, which is has 7 valence electrons, will be we'll have 14. So first we draw a bond, and then we have 12 left. So we have 1, 2, and then we balance it out again. So we start from here. So we add 1 to one side. We have to add it to the other because they're the same element. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 minus 12 is 0. So this works out just perfectly. And then hydrogen only has 2 valence electrons. 1 valence electron each. So each hydrogen has, so hydrogen has 2 valence electrons. So one bond will just satisfy both because each hydrogen has 1, 2, and then this one has 1, 2. So the one with a triple bond has 3 lines in the middle, so obviously the answer is N, or nitrogen. And then here is the last question. Draw the correct Lewis structure for dinitrogen monoxide, aka laughing gas or nitrous gas. And so here, hint, arrange the atoms like this. So N, N, and O. And so we first count the valence electrons. So nitrogen, each one has 5. So 5 plus 5 is 10. Oxygen has 6. So first we connect the bond. So we do a bond. So 1, 2. So there's 4 electrons used right up there. So then we have leftover. So 16 minus 4 is 12. So 12. So we add it 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so we start taking electrons because the middle nitrogen is not satisfied yet. So we take some electrons, but the difference is we take it from the less electronegative one. So if you remember electronegativity, the closer you are to the top left, the more electronegative you are. So oxygen is way more electronegative than another nitrogen, so it's more, but it's not incredibly more. So you have to take electrons from the least electronegative, or least has the least ionization energy because it's easier. So we would end up taking the electrons, the pairs from the nitrogen, and we don't take it from the oxygen because the oxygen is stronger than the nitrogen because oxygen has high ionization energy than nitrogen. So sorry about that, but it's the ionization energy that affects it. So oxygen has a higher ionization energy, so it'd be easier to pull from the nitrogen. So that's why we have 3 bonds from here and only 1 bond from here. And you can always check if each element is satisfied. So 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen is satisfied. 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is satisfied. So all the elements are satisfied. And that brings us to the end of this PowerPoint. I hope that helped you learn about how to draw Lewis dot structures, but it's pretty hard to show it if you don't have papers. But the whole point is just practice this. So when we have diatomic elements, just remember you have to equally add to both sides. So if you add 2 electrons here, you have to add 2 electrons to the other element before you can add 2 electrons to one side. So just think of it as like a seesaw. You have to keep balancing it. But if it's not balanced, then you don't have to balance it necessarily. But the whole point is to get 8 valence electrons all the time. And the next few videos will be about the actual atomic structure, like the 3D structure from after drawing these structural atoms. And then we'll be talking about how covalent bonds can have unequal sharing of electrons, and that brings us to like polar molecules. And so I hope you have a good day, and we'll see you next time.